In the previous lesson, we introduced weighted least squares, where we assumed that the variance of the error term was known. However, in real economic data, the variance structure is usually unknown. So how do we proceed in practice? In this lesson, we introduce feasible weighted least squares, or FWLS. The key idea is simple. If we do not know the variance of the error term, we can estimate it from the data, and then use those estimates to construct weights. This allows us to approximate the optimal weighted least squares estimator. Let us begin with our data set. We have already estimated the regression using ordinary least squares. The estimated regression line is y hat equals 2.39 plus 1.34 times x. These estimates come from minimizing the sum of squared residuals, treating all observations equally. But we know that our data exhibits heteroskedasticity. In particular, the variance of the error term increases with x. This means that observations with larger values of x are more dispersed and less reliable. Now we move to the first step of feasible weighted least squares. We compute the residuals from the FWLS regression. These residuals capture the deviations between the observed values and the fitted values. Next, we square these residuals. Why do we do this? Because the squared residuals provide an estimate of the variance of the error term for each observation.
In the next step, we model the variance. In our case, we assume that the variance of the error term is proportional to x squared. So, we run an auxiliary regression of the log of the squared residuals on the log of x squared. This allows us to estimate how the variance of the error term changes with x. Next, we exponentiate the fitted values from this regression to obtain an estimated variance function. Because we are working in logarithms, exponentiation ensures that our estimated variances are always positive, which is a required property of variance. This step is important. If we attempted to model the variance directly without using logs, we could obtain negative predicted values, which are not meaningful. Using the log transformation avoids this problem and provides a convenient way to model heteroskedasticity. This highlights an important practical point. Feasible weighted least squares depends on correctly specifying the functional form of the variance. If the variance model is misspecified, the resulting weights may be incorrect, and the estimator may lose efficiency. For this reason, economists often rely on robust standard errors when the variance structure is unknown or difficult to model. Robust methods do not require specifying the variance function, while FWLS does. From our data, the estimated variance, sigma hat squared, equals the exponential of the quantity minus 1.376 plus 0.691 times x. This tells us how the variance changes with x. In the next step, we construct the weights. Since optimal weights are inversely proportional to the variance, we take the reciprocal of the estimated variance. So each observation is assigned a weight equal to 1 divided by its estimated variance. Observations with larger variance receive smaller weights, and observations with smaller variance receive larger weights. Now we perform the final step. We run a weighted least squares regression using these estimated weights. This gives us the feasible weighted least squares estimator. The resulting regression line is y hat equals 1.78 plus 1.46 times x. Now let us compare the results across methods. Ordinary least squares gave us a slope of 1.34. Weighted least squares, using the true variance, produced a slope of approximately 1.51. Feasible weighted least squares gives a slope of about 1.46. So the FWLS estimate is very close to the true WLS estimate.
We also observe that the intercept decreases from about 2.39 under OLS to around 1.78 under FWLS. This reflects the reduced influence of noisy observations at higher values of x. What is the key intuition behind this result? Ordinary least squares treats all observations equally, even if some are very noisy. Weighted least squares corrects this by downweighting noisy observations. Feasible weighted least squares achieves the same goal, but uses estimated variance instead of the true variance. This is why FWLS is so important in applied econometrics. It allows us to improve estimation efficiency even when the variance structure is unknown. When the variance model is correctly specified, FWLS produces estimates that are close to the optimal WLS estimator. Let us now connect this with the methods we have studied so far. Ordinary least squares assumes constant error variance. White robust standard errors keep the same coefficients but correct inference. Weighted least squares changes the estimation when the variance is known. Feasible weighted least squares extends this idea to the realistic case where the variance must be estimated. In practice, economists often use robust standard errors as a default. But when we can model the variance, FWLS provides a powerful way to obtain more efficient estimates. To summarize, feasible weighted least squares estimates the error variance from the data, constructs weights based on that estimated variance, and then performs weighted regression. It is a practical and powerful extension of weighted least squares.